All right, so we are still talking about polynomial functions, and we're still talking about the zeros, but we're going to go a little bit more depth today. So the zeros tell you, and we said this yesterday, tell you what input values make the function equal to zero. Zeros are also called roots, so those are like they're synonyms. They mean basically the same thing. One thing we didn't talk about yesterday, but we kind of figured it out, that if x equals a is a 0, then x minus a is a factor. We did it the other way. So we had the factor and got the 0, but we can go both ways with that. All right, so one thing that's new today, but you learned about in Algebra 2 is multiplicity. When you learned it in Algebra 2, it's the first time you ever saw it, and it is probably something you struggled with a little bit. And so that's going to make this year be a little bit easier because it's the same thing you learned last year. So if a linear factor is repeated n times, then n is the multiplicity. So whatever the power is, that is the multiplicity of that factor. All right? And typically, we know that a graph passes through the zeros on the graph. Bless you. It passes through them on the x-axis. So real zeros are also x-intercepts. However, when a 0 has a multiplicity greater than 1, the graph behaves differently near that 0. Okay, so here, whoa, I didn't mean to do that. Here is the equation for this function. All right. So the first factor is x plus 4. What would the 0 be if the factor is x plus 4? Negative 4. And so at negative 4, you can see the graph just passes through the x-axis there. That's typical about zeros. Okay. X plus 1 gives you a 0. What would it be? Negative 1. But when we look at negative 1, it doesn't go just straight through. It actually bends there. And the reason it bends is because of that 3. That 3 means there's a multiplicity of 3. So I'm going to jot that down. And when there's a multiplicity of 3, then the graph bends there. It would also do that at a multiplicity of 5. So any odd multiplicity, not counting 1, there's going to be a bend at the x-axis. All right, and then our last factor is x minus 3. That's a 0 of 3. And if you look at the graph at 3, it bounces. And that's because there's a multiplicity of 2. And that's the case for any even multiplicity. It says that somewhere in the notes. Yeah. An even multiplicity, there's going to be a bounce on the graph. Now, the bigger the even number, there's usually like a wider space on the axis. But if you see a bounce, then you know for sure it's even. All right. And then in that box, I kind of already said this, but maybe not exactly. But the multiplicity of a 0 is the power of its factor. So like we just talked about for this example, for negative 4, you can say it has a multiplicity of 1, but that doesn't really make sense because it's not a multiple factor, so multiplicity doesn't really make sense. But you can, it's not wrong if you do that. But negative 1 has that 3, so that's a multiplicity of 3. 3 has that 2, so it's a multiplicity of 2. All right, so let's do some examples. On example 1, we're going to do a couple of things. We're going to determine the degree of the polynomial, but I'm going to do that last. And we're going to find all the real zeros and state their multiplicity. Now for me, it's easier if I do the zeros first and then go back and do the degree. You can do it however order you want to. All right, so any factor that has an x produces a 0. Every single factor that has an x produces a 0. The first factor I see is this one that has an x. What value of x would make that 0? 0. All right, because that x has a power of 3, then 0 has a multiplicity of 3. All right, the next factor is x plus 1. What should the 0 be for that one? Negative 1. Now, it does not have an exponent, so I'm not going to say multiplicity of 1. You can if you want to, but I'm not going to. So I'm just going to leave it at that. All right, and then our last factor is x minus 4. That's going to be a 0 of 4. And then what about its multiplicity? 2. All right, now whenever you're figuring out the degree, what you can do is just add up all the multiplicities and then all the zeros that there's just one of them. So I would add 2, and then this counts as 1, and then 3. So that's going to be a degree of 6. Whoops. Does that make sense? No? Okay, so you count, when you're counting the degree, for every multiplicity, like that's counted 2 times. So this counts as 2, this is just a 1, and this counts as 3. So you add 2 plus 1 plus 3 to get 6. We'll do more. You'll get it. All right, let's do the next one. Oh, we need to do something before we do that. I'm going to erase that. Sorry, guys. All right, so if you have a factor that will factor more, we need to do that. So x squared minus, or x minus 2 to the 4th is completely factored. Did you have a question?
I was just going to ask, why does the negative 2x3, how does that get a 0?
Of 0?
Yeah.
So you really are just looking at the x cubed. And so if you're trying to figure out the 0, like what would make that 0 is going to be 0. And then it has a power of 3. All right, so then we need to factor x squared minus 4. How does that factor? Yes, that's the difference of squares. All right, and then if you have some factors that are repeated, we would want to bring those together. That helps us with the multiplicity. So it should be x minus 2 to what power? 5th. Good job. All right, so let's see if we can do our degree and our zeros. All right, so we have a factor that's just 3. Is 3 going to give us a 0? No, 3 can never be 0. For there to be a 0 from the factor, it has to have an x, or it's just a number. It's fine. So we're going to go straight to x plus 2. What's the 0? Negative 2. Do I need to worry about multiplicity on that one? I don't. All right, my next factor is x minus 2. What's the 0?
Plus
2. And what's its multiplicity? Good job. So just the power for that factor gives you the multiplicity. Okay, and then when I go to find the degree, this one is counted 5 times. This one is counted 1 time. So what's the degree?
6.
Good. All right, let's look at C. I'm kind of squeezed over here, but this one we definitely need to factor. It's going to take a few steps. Like someone in my last class turned in their work for factoring with just the answers. This is one you can't just do it in your head. So I would expect you to show me some steps here. So on this first one, I'm going to factor out an x first. All right, and then that leaves me with a trinomial that I would just factor Right, and then the second one, I would just go straight to my two sets of parentheses. Now yesterday, when we were talking about factoring, we actually didn't have any where this last sign is a plus. But if this last sign is a plus, what does it mean about the others? That they're the same. And then how do you know what they are? Is with the other one. Very good. So these are going to be both minuses. And then because there's not a number in front of x squared, I want to find numbers that multiply to get 12 and add to get 7. Good job. All right, and then I would go ahead and combine these together. Oops. All right, so from there, I want you guys to tell me the degree and the zeros with their multiples. All right, what did you guys get for your degree? 5. Good. All right, and then your zeros? -2. Through the multiplicity of 2.
0.
0. Good job. Very good. All right, what questions do you guys have? Yeah, you can't forget about the x. The x gives you a 0, 0. I think you might need to move closer to the front. Or get some glasses. He's always squinting. Is your squinting thinking or is your squinting seeing?
It's a confused squint.
Are you good?
Yeah.
Okay. All right, let's talk about imaginary zeros or complex zeros. So some polynomials have roots that contain imaginary numbers. Imaginary numbers do not show up on the graph. So you will not see imaginary zeros on the graph. So if a function only has imaginary zeros, it's not going to have any x-intercepts. And you guys already know that there are functions with no x-intercepts. So here's an example of one. X squared plus 1 doesn't ever cross the x-axis because its zeros are imaginary. And so if we figured it out by setting it equal to 0 and doing the square root, we would know we get imaginary zeros from yesterday. All right? All right, are you good? Are you sure? Okay, I'm pulling up the answers from yesterday, and this is going to help us with the next part. So yesterday, every time we had an I, there was a plus or minus in front of it. So 4i and negative 4i were solutions. I squared of 7 and negative I squared of 7 were solutions. 2 plus 3i and 2 minus 3i were solutions. Our real numbers didn't work out that way, but anytime there was an I, there was always 2 that went together. And that is no coincidence. That will always happen. So imaginary roots or zeros come in conjugate pairs. Always, always, always. And so if a plus bi is a root, then its conjugate is a minus bi. So if there's 2 numbers, the number that just has a real part, doesn't have an I, stays the same. The imaginary part is always opposite for conjugates. All right, so this was actually one of the ones I just talked about. So for I, we're going to determine what its conjugate is. So it's going to be negative 4i. What do you guys think about I? Or sorry, negative I, would just be I. Good. Okay, these are slightly more difficult. So 2 minus 3i, its conjugate, 2 plus 3i, good. So the real part is the same, the imaginary part is opposite. They always come in pairs. Now sometimes questions are written in a way to trick you, like the one we're about to do. It'll just give you one of those imaginary roots, and you have to know its conjugate is also a root. All right, that takes us to the fundamental theorem of algebra. So algebra, everything you learned in algebra is to get to this theorem. And so this theorem, this isn't like quoting the theorem, but a good way to say it. So a polynomial of degree n has exactly n complex numbers when you count the multiplicities. And so counting all the real zeros, all the imaginary zeros, and then each real zero that has multiplicity is counted multiple times, that will always give you the degree of the polynomial. All right, so on example 3, we have this function f. So looking at f, what is a 0? Negative 1. Does negative 1 have some kind of multiplicity? An even multiplicity. So let's say it's a multiplicity of 2. It could possibly be 4 or 6, but we're just going to say 2. All right, what else is a 0? 3. Does it have any special multiplicity? It doesn't, because it just goes straight through. So it's just, we count that one time. All right, so it is also known that x plus I squared of 3 is a 0. So if, I said that wrong, x equals I squared of 3. So if x equals I squared of 3 is a 0, what else is a 0? Negative I squared of 3 is also a 0. Right, and so the question is, what is the least possible degree for this function if it has those zeros with those multiplicities? 5, yeah. So this one is counted twice, once, once. So n, the least possible for n would be 5. The only reason we say least possible is because this could actually have a multiplicity of 4 or 6. So we chose the least possible multiplicity for it. Does that make sense? It's okay. So another possible value for n for the degree is if we said that was a multiplicity of 4, it could actually be 7 could be the degree. Yes. So n is the degree. So it's just saying what's the smallest degree for this function. All right. What other questions do you guys have? Okay. You have some time to work on your assignment.